Well, we have been exploring radical expressions, square roots, higher order roots, exploring how we simplify those things. Well, now we're going to take it to the next level by multiplying radicals. And we've seen this before, this property of radicals that says the square root of a times the square root of b is equal to the square root of a times b, which basically means that as long as you have the same index, which means they're squares or cubes, right? They're the same thing. As long as they're the same and you're multiplying them, you can just multiply the radicands, which are the things that are on the inside. So, for example, the square root of 3 times the square root of 2 is equal to the square root of 6. Now, you could even take a calculator and check that and prove it to yourself. Sometimes, and most of the ones that you're going to see involve more than that. They involve some simplification as well. So the square root of 3 times the square root of 3. Now you can even pause and logic your way through this, is equal to, well, first we could take it to the square root of 9, but then take the square root of 9, which is just the number 3. So the square root of 3 times the square root of 3 is equal to 3. Well, we could take the square root of 10 times the square root of 5. And one thing that you might notice, you'll start to observe this as you get more comfortable with these. This has a square root of 5, and the 10 has a square root of 5 like buried inside of it as a factor. And you might even take a guess on what that might do in the long run. We'll start just by multiplying these two things and say that 10 times 5 is 50. But then we always want to simplify if possible. And as we've learned previously, we take the 50 and we split it up. We split it up into two factors, one of which is the biggest possible perfect square. And so we really think about the square root of 50 as the square root of 25 times 2. And then we can take the square, I'll keep doing it as I've been doing it before. We can break it apart into two separate radicals. Square root of 25 times the square root of 2, which is basically the opposite of this rule. It's going back to this way. And then we look and say, okay, what can we take the square root of? This one, we know that is 5. So we can fully simplify this to be 5 radical 2. This is 5, and this stays on the inside. And then that is our simplified expression. Now, is that what you would guess would happen from back here when you notice there was a 5 here and then there was a 5 in there? That's what happens. Now, sometimes we have coefficients out front. Coefficients. And you might see something like this. 2 radical 2 times 3 radical 14. Now I always like to have you pause and take a guess. Guess what might happen here. What do you think you might do? Make a prediction. So we take the coefficients here and here, and we multiply them, right? We would say that is 6. And then we do the same thing with the radicands. 2 times 14 is 28. But then we see if we can simplify that even further. We know we have that 6 out front, but then we look inside the 28 and we break it apart into 4 times 7. Why? Because 4 is a perfect square, and it's the biggest possible perfect square. So what we end up with is 6 times the square root of 4 times the square root of 7. We can take the square root of 4 and make it a 2. And then we could finish this off by multiplying the 6 and the 2 to be 12, and we still have the radical 7. So anything that ends up outside of the radical, any numbers, those just get multiplied. And we end up with 12 radical 7. So try this one on your own. 3 radical 6 times 4 radical 12. See if you can work through that on your own. Pause the video. I'll keep going. So we have 3 times 4 on the outside. Those are the coefficients, which is 12. And we have 6 times 12 on the inside, which is 72. And then we leave that 12 outside. We split up 72. Now, you might initially treat this as 9 times 8. But if you examine it further, you'll see that 8 actually has another perfect square inside of it. So the better option is 36 times 2. Then we can separate it into 12 times the square root of 36 times the square root of 2. We take the square root of 36, which is 6. We do 6 times 12 here and here, 72, radical 2. 72, radical 2. Now, sometimes when we are doing these, we have really big numbers under the radicals. And you might want to take a slightly different approach to those, like the square root of 75 times the square root of 32. So it doesn't make a whole lot of sense for you to take and multiply 75 times 32 to get 2,400. That might not make a lot of sense for you to do. What might make better sense is to just start off by putting them under one radical and saying, I know this is 75 times 32. And then just start breaking apart those numbers to see what happens and explore these factors individually. So we might look at this and say, well, 75 I know is 25 times 3. Might take you a minute to get there. In 32, if I look for that biggest perfect square in there, we can say that it's 16 times 2. Well, what we end up with here is, I'm going to work it right underneath it, the square root of 25 times the square root of 3 times the square root of 16 times the square root of 2, which gives us 2 radicals of perfect squares, which we know are 5 and 4. Multiplying those, because those are now outside the radicals, 5 times 4 is 20. And then on the inside, we have 3 and 2, which is 6. And this is completely simplified. That is completely simplified there. Another one, well, actually, let's pause and you can try this one. The square root of 80 times 3 radical 50. So why don't you pause the video and try this one on your own. I will keep going. So what we'll have here, we've got one coefficient. So that's just going to stay out front, right? This 3 doesn't have anything to multiply by. It's going to stay out front. But on the inside, we have 80 times 50. Okay, so what's going to happen there? We've got our 3. And then we have to start separating the 80 and the 50. Well, if we work it far enough, we find that 80 has a 16 and a 5. 16 times 5. 16 is that biggest possible perfect square. And 50 is 25 times 2. Now, as you get more sophisticated in this work, you don't always have to break this next step down into 4 individual radicals. I think it can help when you're learning it. But what a lot of people end up doing is once they get it to this part, they see, oh, I've got a 16 there and a 25 there. And they immediately just jump to taking the roots of those and pulling them outside. So what we have here is our 3 times the root of 16 is 4. The root of 25 is 5. And then you leave the leftover stuff, which is the 5 times the 2. And then we just put it all back together and simplify it. So on the outside, we have 3 times 4 times 5, which is 60. That's this stuff. And on the inside, we have 10. 60 radical 10. Is that what you got? I want to show you just one more scenario that can occur sometimes. And this one has some weird-ish looking numbers. I've got the square root of 51 times the square root of 21. And so again, these are some big numbers. And if you multiply those, you get something really big, over 1,000. And so it's probably going to be better off if you just keep them separate and treat it as the square root of 51 times 21. And then you look to break those apart. Well, if you look at 51, 51 is only 3 times 17. That's the only way to break up 51, is 3 times 17. And there's no perfect square there. Same thing with 21. It's just 3 times 7. There's no perfect square inside that 21. But what do you notice? You have two of the same number in here, a 3 and a 3. So if we think about it like this, we've got our 17, we've got our 7, but then we have 3 times 3, which is 9. By doing that and pairing up these non-perfect squares that actually match, then we can end up with a perfect square inside of that radical. And what do we do next? Well, we take the square root of that 9 and we pull it out to the front, which is 3. And then we multiply whatever 17 times 7 is. And 17 times 7 is 119. So we end up with kind of a big weird number inside that radical because we started with some weird numbers, but you do see that they had matching factors in there. So this one ends up as 3 times the square root of 119. And that is how we multiply with radicals. We multiply what's inside and then we simplify as possible.